Hello, it's Keith here, and this is lesson 102 of the platform-specific series of Modular assembly programming tutorials. We're looking at MaxTile, which is my multi-platform software tilemap, and it is a software tilemap today because we're running on the Sam Coupe and we're using the bitmap mode, the 16-color bitmap mode. Here is the example here. We've got a moving object and it can X flip and Y flip and X and Y flip. Now this is all done with the tilemap. We've got simulated sprites which are actually also done with the tilemap. You will notice there's some garbage around the corners of the screen, and that's because the tilemap code we're using today can only draw one full tile. Now the intention is in an actual game what you would do is you would do a border of 3 bytes on the edges to cover that up, but I've not got that implemented today. Now this is the 16-color version, so the tile patterns are using 16 colors. We're going to look at next time at a 4-color version as well. I like to use 4-color patterns because they're 16 bytes rather than the 32 today's is using. Saves a lot of memory, and it makes things a bit easier on 64K systems, but it also makes it a lot easier to port games between a lot of different systems, because if all of a sudden all of your pattern data doubles, what was perfectly possible on a 4-color system suddenly becomes impossible on a 16-color system simply because you've run out of memory or you can't page flip enough to get the data in. Anyway, let's go over to our code. Let's take a peek. Okay, so the files we're going to be looking at today are the example that you just saw, the Sam MaxTile mid, and also the 16-color version Sam V1 MaxTile normal. Now, to enable the 4-color version, we just uncomment this line here. That will switch to the 4-color version. Now, I'm not going to discuss how MaxTile works. I've got an entire tutorial series on that. It's just the Sam Coupe graphics code we're looking at today. So we've got various setup for the memory that MaxTile uses. The one that we're really interested in is the lookup table here. Now we've got flip-LUT here. On the Sam Coupe, with the version we're looking at today, this does the X flip. On the 4-color version, it actually does the color conversion as well, but that's not the case for this version. So if we just look at the flip-LUT code here, so basically all we're doing is we're swapping the top and the bottom nibble, which are the 2 pixels, and this is basically swapping those pixels within the byte. So that is performing the X flip operation, and we'll be using that later on in our program. Now at the end of our program data here, we have the bitmap data. Now there's a special kind of tile which is solid fill tiles, and these just use 2 bytes and they repeat them every other line to create a kind of checkerboard effect. So those are 16 colors, so they just use 2 bytes. However, the other tile patterns in 16 color mode use 32 bytes each. Now we've had to space these out with some org statements, and that's so that the tile patterns have the correct locations for the tile numbers that are defined within our character miniature tile maps, which are simulating sprites, and also the background itself. So that's why we've got those, and that is the bitmap data we're using there. And we've also got palettes there and various other bits for the function of the example. The example is also covered in the MaxTile main series, which covers the multi-platform code. It's only the platform-specific code we're looking at today. Now, when we're drawing an entire tile map to the screen, we use the screen-based parameter, and that is pointing to memory address 8000. So that is the VRAM base. The top left corner of the screen is at memory address 8000. Our program code is actually running starting from the quadruple 0 range. We actually load in at 8000 and copy the bank. We bank switch the bank into the low bank. That's because the default is it loads at 8000 because of the operating system at memory address 0, but we want the 0 range to be free for an interrupt handler and the IM1 interrupt handler potentially. So that's why we're doing that kind of page flipping around. So we're page flipping in the correct VRAM there. We've got our VRAM base with the screen-based parameter here, but whenever we want to draw a sprite, or a simulated sprite I should say, we use this getScreenPos function here. And this takes the X and Y coordinate and it calculates the VRAM destination. It's very easy on the Sam Coupe. Each line is 128 bytes, 256 pixels, and so the lines are in linear order, which we like if we can have it. We can't have it on some systems like the CPC and the Spectrum, but on the Sam Coupe we can have it. Very straightforward then. So all we simply do is we take our Y position in logical units. Now logical units in my tutorials always means pairs of pixels these days. So basically we need to increment the H part of the HL VRAM destination by 1 for every 2 lines, and because we're working in pairs of pixels as logical units, we've already done that. So we actually just take the Y coordinate, add our VRAM base, and that is the H coordinate. Now the L coordinate is the X position in bytes. Each line is 128 bytes, and because we're working in pairs of pixels, our X coordinate is in bytes already. So again, we load the L coordinate from the L byte from the X coordinate, and HL is now the VRAM destination. Very straightforward on this system. Very nice indeed. What is Slightly less nice though is the speed of the system. The speed is not bad, and MaxTile is designed to work on bitmap based systems that aren't very fast. The Amstrad CPC isn't very fast. But while the Sam Coupe has a 50% faster processor, it also has a 100% bigger screen than the Amstrad CPC, so it is a little bit slower, but it's not too bad, and we've optimized our code as best we can to increase the speed. Now, the draw tile routine will only be executed if the position in the tile map has the update flag set. Our tile map is pointed to by the BC register pair, and the first byte in that, the least significant bit, is the update flag. And if this is set to 1, this tile needs to be redrawn, either because we've scrolled the screen or because a sprite that was in that position has moved away or whatever. So that will cause this to be executed. If that update flag was not set, the draw tile routine will never have been executed. And at this point, the update bit has actually been shifted out of the byte that's in memory, and we shift back in a 0 to clear that update flag down here. Something that's important to notice. Now, what we're doing here first is we're checking the new bit 0, which was the bit 1, and that is the program flag. Now, the draw tile routine works as a sort of a binary tree. Basically, I wanted to get to the simplest, most common task as quickly as possible, and there's branches out to do more complex, rarer tasks that happen later or not at all. And so the most common task is to draw a simple unflipped tile, which is the vast majority of the background tile map. So in that case, we've got our low byte. Now, the top 4 bits of the low byte are actually the tile number in most cases. They do have some other functions in some cases, but generally they're the tile number. We add to that the second byte, which is the high bits of the tile number, and so the 4 bits there and the 8 bits there become the tile number effectively pre-multiplied by 16, because this is designed and optimized for a 4-color system. However, this time we have a 16-color system, so rather than 16 bytes per tile, we have 32 bytes per tile, and that means we have to do 1 extra pair of shifts here to effectively multiply our tile number by 32. So that's what's happening there. So H and L is the offset now for the tile that we want to show to the screen. What we now do is we add D and D, which is the tile base, the base of the bitmap pattern data for our tile definitions. And then we move that into the stack pointer, because draw tile uses stack misuse to quickly read data. Now, we're going to draw 8 lines to the screen, and we know that we're aligned to a pair of lines because we work in X and Y coordinates of logical units, which are pairs of pixels and pairs of lines. So we can't be on an odd line, and so we can use that in our coding to make our coding more efficient. Now, what we're going to do whenever we move across the screen is we simply increment the low byte of the HL pair. When we move down a line, we'll either need to change the top bit of the L coordinate, and so we would be effectively adding 128, or we'll have to basically clear that, and then we'll have to increment the H coordinate. So if we've basically overflowed, so if we were at memory address 8000, we would add 128, and then the next line would be 8080. Then we'd add another 128, the L byte would become 0, and then we'd have to increment the H byte. Now, to make all of this a little bit quicker, what we're going to do is we're going to pre-calculate the 2 possible values of the L register when we move down a line. So either the top bit will be clear or the top bit will be set, and we're loading those into B and into C, and that's how we're going to quickly move down a line. So what we're going to do, we're going to pop a pair of bytes out of our source pattern data, so that's the equivalent to 4 pixels. We then write those to the screen, incrementing L, moving across the screen a byte each time. Now, once we've done our first line, we then load the L register from C. This moves us back and moves us down a single line. So now we do the same again for the next line. We then pop the 2 bytes again, writing them to the screen in the same way. This time, rather than loading from C though, we load from B, and that moves us to the next line, 2 lines down from the original starting position. But this time we also need to increment the H register, so that's what we're doing there. We then do the same again, loading L from C, do the same again, loading L from B, incrementing H, and we do this a total of 8 times, or 4 times if you're considering them to be pairs. Once we've done an entire line, basically we need to move back to the left, we need to move up back to the start of our tile, and we do that by decrementing H 3 times. The L byte has already been cleared up there, and then we return. Now, there's an awful lot of data here, and this is what's known as an unwrapped loop. So basically, we could loop this part 4 times, and that would have the same effect. But because we've got a bit of a speed issue compared to a system like the Amstrad CPC that had its own speed issues, I've decided to unwrap this loop, and basically I'm sacrificing memory for speed here. So you could make a different decision. You could make an optimized version of this that repeated that part twice, or you could even optimize it even more if you wish. But as I say, I felt this was the appropriate balance between performance and memory here. So that's what I've done. Now, if that program flag was set here, bit 0 as it's tested here, but it was originally bit 1 in the source before the update bit was shifted out, we're using some kind of advanced drawing routine, so not a regular unflipped tile. Now, the first thing we want to think about is maybe this is an X or a Y flipped tile. So we're checking these two bits here, which are the X and Y flipped bits. If both of these are 0, though, this is what's known as a custom tile, which is a special program. If we get to this point in our code, though, it is some kind of flip, an X flip, a Y flip, or an X and Y flip. So what we're first doing here is, because we've messed with the accumulator here, we're now clearing the update flag in a different way down here. But then what we're going to do next is we're going to calculate our pattern source, because we don't know whether we're X or Y flipping yet, but we know that we're going to be working with regular pattern data. So again, we're taking the pattern number, multiplying by 32, adding it to DE, and moving it into the stack pointer. We're going to this time actually use some optimization. So rather than unwrapping the loops, I'm using a loop count in pairs of lines here. So we're going to do 4 pairs of lines for our 8-pixel tile. Now, what we're actually going to do, though, is going to depend on the bits of the first byte that was read in from the tile map. So here we're checking bit 2, and this is the Y flip flag. If this is clear, the fact that we've got here, we know we're doing some kind of flip. If we're not doing any kind of Y flip, we must only be doing an X flip. So that's what we're going to do here. We do 2 things. We move to the right-hand side of the tile pattern, and we're going to draw the bytes onto the screen backwards. But we also need to flip the data within those bytes, and we do that via our lookup table. Very simple. All we do is we load the B register with the address of our lookup table, the top byte, and then we read in our data from our source by popping it as before. But then we load the byte that we want to flip into C, and we read in from BC into the accumulator and write that to the screen. And the reason we do that is because the way we calculated our lookup table is we took the L byte of the HL address as the source that we wanted to flip, and we flipped it, and then we stored it at the resulting address at that HL address. And because we did that, effectively anything we load into C here, when we load from BC, we get the flipped equivalent. And so that's what we're doing here. So that's loading that flipped equivalent here of the E byte, and then writing that to the screen, and then doing the same for the D byte. We're moving down the screen in a different way this time. We don't have any spare registers to pre-calculate those. So we're effectively adding 80 plus 3, and that's moving us down a line and moving us across to the right-hand side of the tile again. We're repeating, adding 80 plus 3 again, and this time incrementing the H register. We've now done a pair of lines. So we decrement our loop count, which is now in the shadow registers, because we flip to the shadow registers up here. And so we're decrementing our loop count and repeating until we've done 4 pairs of lines. Once we've done that, we're finished. We move back up to the top of the tile. We move to the left of the tile again, and we repeat, returning to the calling routine. We don't use calls and returns because we're using stack misuse. So that's how we X flip our tiles. When we're doing our Y flip, we end up down here. Now, the first thing the Y flip's doing is checking if we're also X flipping, because we might be X and Y flipping. So a Y flip is very straightforward. We read the source data in the exact same way as we did before, but this time we write it to the bottom of the tile and we move up the screen. So here we're moving to the bottom of the tile here, and this time B and C are free, so we're pre-calculating our Y coordinates for the L register again, and then all we're doing here is we are writing them to the screen. But then after we've done a line, we're basically using the B register this time instead of the C register, so that's moving us up a line. And then when we've written the C register to L, we're decrementing H, so that's moving us up the screen here. As I say, we've got an unwrapped loop here just to save some memory, because I'm assuming you won't be X and Y flipping as much as you're drawing unflipped tiles, but maybe I'm wrong. I mean, again, it depends on what your priorities are, how you should do things. Now, the X and Y flip routine are very straightforward, so this does both tricks at the same time. So here we're moving to the last line, here we're moving to the right hand side, but then basically we're doing the same as we did with both Y and X flips. So we are using our lookup table to convert our source data, but then we are moving up the screen. Again, the BC register is not available for us this time, but we are moving up the screen here, and so we're drawing from right to left, flipping the source data and drawing up the screen for our tiles. Now, that's all of the basic tile types. Flip tiles are relatively basic. The final ones are the so-called custom programs. So these are the sort of clever ones that do things that I thought might be useful. So basically, the example code I've got here has 3 different kinds of custom. That means there's actually one free. But the first one is filled tiles, which is where we use just 2 bytes drawn to the screen repeatedly. Saves reading, thus saves time. So that's a little bit faster. So if you want to fill larger areas of your game, that will make things faster. We have double height tiles. You can see those kind of stretched tiles there in the background. Those are regular tiles that have been just drawn using 16 bytes on this system rather than 32. It was actually meant as a space saving, as to save pattern data and fill the screen with bitmap data, just saving a little bit of memory. But it will also be a little bit quicker, I think, and it also gives a cute effect. Maybe the old Metal Slug games used to stretch bytes quite a lot, and it was because it was something that the Neo Geo could do in hardware. So maybe a cute effect as well if you want to make a character suddenly get bigger. But the final one is pseudo transparency, and that is being used by that character, very effectively being used by that character here. You can see it's not being used at all by that character there. I'm using something called 0 byte transparency, which is where if a byte that's read in from the source pattern is entirely full of zeros, it's basically entirely 0. We don't draw it to the screen, and that gives a kind of a sort of an edge around the tiles, but the sprites. But to be honest, on the Sam Coupe, with just 2 pixels per byte, you don't really notice it. On a 4 pixel per byte, you got to get a kind of chunky border, but it's not something I particularly dislike. But as I say, on the Sam Coupe, it actually works extremely well. So what we're doing here is we're getting the command bits. Now the command bits are basically these 2 bits here, and so the memory layout for the tile number is actually different. This time the top 2 bits of the low byte are the high bits of the tile number here, and that's because basically the second byte is the low bits of the tile number, and the 2 bits that were the low bits of the tile number are now the program number, which are these bits here. So we're taking those 2 bits here, and we're then going to consider what they are. So we're either doing a fill, a transparent tile, or a double height tile. Let's look at a double height tile first. So what we're doing here is we're multiplying our tile number by 16 because we're using each line twice, so rather than 32 bytes it becomes 16. Adding our bitmap source because we're using the same bitmap data. We're working in pairs of lines here. And then basically what we're going to do is we're going to read in a pair of bytes from our source pattern, but then we're going to draw them to 2 neighboring lines simultaneously. So we write the E byte to the HL pair, set the L register, and then we've now effectively moved down to the opposite byte of the E pair. We write again, we reset, moving back up, and then we move across. We do the same with D, moving down and moving up. And then we do the same for the second pair of bytes. There's 4 bytes on a line. And then basically we've now done 2 lines. So we load L from B here, resetting with the pre-calculated value there, and we move down to the next pair of lines, and we repeat until we've done all of those double lines. The fill command is sort of similar here. That's actually wrong. That's the tile number times 2, not times 32. Apologize for that. So that's calculating the bitmap source here, and basically all we do here is it's sort of a very crude version of the normal draw routine. We pop just 2 bytes for the entire tile here, and we write the E byte to the first line, move down a line, and then write the D byte, and we just repeat that 4 times, and that's our entire tile done. So far less reading. So as I say, those field tiles should be far faster, and you would be best to use those as much as you can if your game is getting a little bit slow, and if you're having sort of heavy scrolling, it probably will be. So that's that. The final kind is the transparent tiles. Now there's 2 kinds of transparent tile in all honesty. If you look around the Eureka character's feet, it has no tiles drawn around its feet there. That is a completely empty tile, and that is defined by a byte of 255 here. And so we're checking that by incrementing the byte read in. If it's 255, we're drawing nothing, and we simply skip back to the done routine. However, anything other than 255 is a partially transparent tile. So in that case, we're going to use the regular pattern data. So we're multiplying our tile number by 32 here, adding the tile number base, pre-calculating the offsets again here for our line numbers. And then what we're going to do here is we're going to pop a pair of bytes out of our source pattern data, but then we've loaded the accumulator with 0, and the 0 here is the byte we're going to compare to. So if the byte we've read in is matching the accumulator, we're not going to write this to the screen, and we're just going to skip across leaving that byte unchanged. You can see we're repeatedly doing this for all of the bytes in a line here, in a pair of lines actually. And so this is basically not drawing anything that's got a byte 0 to the screen, and that's how we achieve our 0 byte transparency. Now the reason I've loaded the accumulator with a 0 here, I'd usually use XOR A, which is a quick way of setting the accumulator to 0. But maybe you don't want to use 0 as your transparent byte, maybe you want to use 255, or maybe you want to use some completely random combination of bits here that you think will never happen in your actual game. So just change this value here and your transparency will work in a different way. So there we go. So that's how this code works, and that's all of the options that I've used for my MaxTile routine. MaxTile is by no means the best. It's not intended to be. It's intended to be multi-platform and work in on a lot of different systems. I'm now building it into another programming project where I'm writing a multi-platform graphics gaming engine, which actually uses a virtual machine for its logic code, and that means it's not just multi-platform on a single CPU. It's actually multi-CPU as well. And part of the necessity of that is you have a graphics routine which works in the exact same way on every system, whether it's a hardware tilemap or a software tilemap, whatever its screen capabilities are. You just need code that will do the same thing when asked to do, when given the same source data, and that's what MaxTile is designed to do. There's a lot of other code behind this that I've not covered today. I've just covered the drawing routines. There's a whole tutorial series on those, but I would fully understand if it's too much for you. Simply don't, if that's more than you need, just don't use them. I mean, it should be pretty trivial for you to take the example code you've seen today and build that into your own tilemap drawing routines. You know, take the bitmap drawing routines, if the X flip, the Y flip, if you need them, the fill routines, and just work them into your own code, or just use inspiration of the things I've done that maybe will help you out in your own in programming. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.